Hello, my name is Andrew Poehler. This voice is robotic. For more than a decade, my research has focused on Kolmogorov-Arnold networks. In this video, I will discuss recent advances in this field and demonstrate the key advantages of these networks, particularly with respect to training speed, model compactness, and implementation complexity. Before proceeding further, I would like to present a single benchmark example demonstrating the practical capabilities of this approach in both scientific research and real-world applications. The benchmark dataset contains 500,000 randomly generated tetrahedra, while the target vectors correspond to the areas of the tetrahedron faces. The network training time is approximately 1.5 seconds on a standard CPU. The complete C++ implementation requires only 340 lines of code and uses no external libraries. The implementation is fully reusable and sufficiently general for integration into larger applications, and this lecture covers all critical details necessary for practical adoption. The network can be viewed as a tree of functions. The objective of training is to determine and optimize these functions in order to achieve the best possible mapping between input features and target values. Several training methods exist for this type of network. In this video, I will focus on the Kaczmarz method. The choice of function type depends on the modeling objective. When the primary goal is maximum training speed, piecewise linear functions provide the best performance. From the perspective of an individual function within the network tree, only 3 operations are required: interpolation, update, and numerical derivative evaluation. Interpolation and numerical differentiation are straightforward operations. The update operation consists of moving a single segment to a new position in order to reduce the residual error. These operations are illustrated in the following animation. First, the corresponding segment is identified. The left and right control points are then shifted according to their relative offsets with respect to the new target position. The complete training process is therefore reduced to repeated application of these 3 operations to each function in the network tree for progressive compensation of the computed residuals. We now move from the level of an individual function to the level of an entire layer. A layer represents a vector-to-vector mapping implemented by an organized set of functions. The interpolation operation is part of the forward pass, or inference stage. For the output layer, we compute the residual vector, denoted as delta y, and update the layer accordingly. In practice, this means that each function within the layer receives the input vector x together with the residual error and the learning rate parameter. For intermediate layers, the residual errors are propagated backward through the network using the Jacobian matrix, which is straightforward compute for piecewise linear function types. This backward propagation of residual errors forms the foundation of gradient descent methods, which have been widely used since the middle of the 20th century. It is important to note that, for networks of moderate size, these matrices remain relatively small, and the computation requires only matrix vector multiplication and not matrix inversion. This demonstration illustrates the overall training logic of the network. The forward pass propagates information from the input vector y through the hidden vector z and finally to the output vector u. Residual errors are then computed for each layer, after which all layers are updated accordingly. Although this example contains only 2 layers, the same training procedure naturally extends to networks with a larger number of layers. There is one additional issue that must be addressed: renormalization. A layer consists of multiple parallel blocks, where each block performs a vector-to-scalar mapping, as highlighted in yellow. The function g operates within a limited domain, and during the update process the computed argument, denoted as y-hat, may move outside the valid range of definition. This problem has simple solutions. 2 possible approaches are shown here. The first method applies an additional update operation whenever the computed value of y-hat falls below or exceeds the allowed limits of the domain. The second method maintains adapted domains for each block using variable minimum and maximum limits, followed by a simple linear mapping into the fixed domain of the upper layer. The pseudocode for this approach is presented in the lower section of the slide. The significant training speed advantage of this method naturally requires an explanation. The underlying optimization approach was originally introduced by the Polish mathematician Stefan Kaczmarz in 1937. Geometrically, the method can be interpreted as a sequence of projections onto hyperplanes. The inference step for an individual function can be formally represented as an inner product involving a sparse vector containing a large number of zero elements. Although both the arguments and the function values change during training, the sparsity structure itself remains preserved. A single block within a layer can therefore be represented as a long sparse vector, while the entire layer becomes a set of parallel sparse blocks, and hyperplanes used in projections are mainly pairwise orthogonal. The numerical coefficients in the vector represent relative offsets from the left and right endpoints surrounding the argument x. These coefficients are normalized by the width of the corresponding interval, and therefore their sum is always equal to 1. This animation illustrates the concept of projection descent onto orthogonal hyperplanes. It is geometric interpretation of the rapid convergence of the Newton-Kaczmarz method. Kolmogorov-Arnold networks possess an interesting property that is generally not available in conventional neural network architectures. Multiple models with identical structures can be averaged to produce a new model that preserves important properties of the original components. This property was originally observed in the field of federated learning, where local copies of a model are trained on proprietary datasets and later merge into a global model. The simplest form of parallel training follows an iterative procedure. Multiple copies of the same model are created. Each copy is trained on a separate data partition, and the resulting models are then averaged. By repeating this process iteratively, the final model can achieve accuracy comparable to direct training on the complete dataset. Now I explain the most advanced part of it, which involves field-programmable gate arrays and integrated circuits. These devices often use fixed-point arithmetic, which is similar to integer operations. Another limitation of FPGA implementations is division, which is computationally expensive. Therefore, effective use of FPGA boards typically requires models that rely mainly on integer parameters and operations, preferably with minimal or no division during training. Fortunately, KNs allow this. Features and targets can be risk-scaled to integer values. The function node points can also be represented as integers. The domains of the inner functions can be chosen arbitrarily. After training such an integer-based model is completed, it can be risk-scaled back to the original feature and target scales, as well as to convenient domains for the internal functions. Here is a simple example of risk-scaling nested functions to match the domain of the outer function. This figure illustrates the most frequent and critical operation in the proposed logic adapted for FPGA implementation. Since the function domains can be freely chosen, the width of each linear segment along the x-axis can be selected as a power of 2, which allows division to be implemented as a simple bit shift. In the same way, the computation of the offset can be efficiently obtained using a bit mask operation. The update step then uses this offset in standard multiplication and addition operations. Another convenient property of FPGA hardware is the support for arbitrary integer bit widths. Values do not need to be restricted to 32-bit or 64-bit representations. Instead, bit widths can be chosen freely to ensure numerical stability. For example, 13, 17, 47 bits, and so on. The image below shows a simple FPGA board used for a prototype implementation. Its cost is only a few $100s, and it is suitable for testing purposes rather than production deployment. The amazing thing about FPGAs is extreme hardware-level parallelism, with thousands of elementary operations executing simultaneously. You describe this parallel behavior using a different style of assignment: no threads, no joins, no synchronization worries. In the third line, you see two assignments executing concurrently. This is called non-blocking assignment, and you can have thousands of them, limited only by the available hardware resources. The FPGA systems operate in clock cycles. The amount of parallel computation that can be performed within a single cycle is determined by the available hardware. In an idealized scenario, a full forward pass for one layer can be executed in a single cycle, followed by the next layer in the next cycle. Propagation of residual errors may require additional cycles, and a full update of the model may require one more cycle. However, this represents an optimistic lower bound. In practice, The implementation typically requires more cycles per record, often in the range of 15 to 25 cycles. In my own running implementation, I managed to process one record of 2-layer KN for 15 cycles. Modern FPGA boards operate at clock rates on the order of 100 to 500 million cycles per second, and some even more. Under these conditions, achieving processing rates of around 15 million records per second is realistic. This work has been conducted as freelance research without affiliation with any research laboratory or institution. Here are the timestamps of my open-source system Verilog code. The first version was published in January 2026. More details can be found on the website openkn.org. The source code used for all benchmarks shown in this video is available at the provided repository link. The second link contains the RTL implementation of the FPGA demonstration. The concepts presented in this video were developed and implemented by Mike Poluektov and Andrew Poehler. Most of the material shown has been published in peer-reviewed journals by Springer and Elsevier. For a full list of publications and additional information, please visit the website